So welcome back. This video is going to really start talking about number 2, so using k-means, as well as some of the issues under 3. So back in the first video, for clustering, we're going to assume that we've observed n observations. So these could be subjects, they could be objects. Anyway, we've sampled n of them, and we've taken p measurements on each object. I'm also going to assume that this matrix is complete, so we don't have any missing data to deal with here. I'm going to assume that these x's are numeric for now, although when we get to latent class analysis and the general finite mixture model, we'll relax that. Finally, I'm going to use an x sub I to indicate the row vector of measurements for subject I. So back in the course packet, instead of putting an arrow over x, I'll just make it boldface. And from now on, we're going to understand that to mean row vector for subject I. K-means clustering assumes something called hard assignment. So hard assignment is where every observation is assumed to have come from exactly one class. So these classes are going to be labeled 1 through k. The only difference between this and ANOVA is that with ANOVA, we knew which group you're in. So I would know which treatment I administered to each person. In the case of clustering, these group assignments are unobserved. Not only do I not know these group assignments, I also don't know how many there are. So I don't really know what big K is. What we tend to do with clustering is select a ballpark number for K. Like maybe I'm interested in 5 to 8 clusters. Then we go off and we run different cluster solutions. So I go set k equal to 5 and go find the 5 cluster solution. Set it to 6, go find the 6 cluster solution, and so forth, and compare the cluster solutions. So in general, we set k before we estimate the model. Then we examine how well that model fits the data. I'm going to let script c sub k denote the indices for all members of group K. So you can write this in set notation as the set of all I, such that this group identifier is equal to some little k. So for example, if I had n equal to 100 observations, maybe observations 2, 4, 7, 19, 32, and 52 belong to cluster 3. So then this set would be the observation numbers that I just mentioned to you. The grand mean of the data, so think of this as we don't have any clusters, we just have one giant mass of data, will simply be the average of all these row vectors. So x bar is also going to be a p vector, and I compute the sum of these individual. The cluster mean, alternatively, is going to be x bar sub k, and this will be boldface. That will be understood to be a p vector. I'll find these cluster means by simply averaging my x's. I find these cluster means simply by averaging all the observations that are assigned to that particular cluster. So having found the cluster means, we often want to assess how good that cluster solution is. The ways that we're going to assess the quality of the cluster solutions start with different sums of squares. So the total sums of squares is how far is every observation from the grand mean. Within is going to be how far is each x from the respective group mean. And then the between group sums of squares simply says how far is each x bar from the grand mean. Let's go back to the picture that I drew during the first video. So the average of all these cases, let's just put a little x about there. We're going to call that x bar, if this is cluster 2, go back to numbering them since that's what I seem to have been doing. This is going to be x bar 1, and then this is going to be x bar 3. The grand mean of everything would be average all of the cases, and that would be some observation right here. So let's just call that x bar, the grand x bar, you can put the dots indicating that you've averaged over groups and individuals. What SSB says is, what is the variation between the cluster means? So how much variation is there between these cluster means? So it's going to be the sum. So we can think of this as the sum of the number of cases in a particular cluster. So using that's the ANOVA notation. This would be the cardinality of group K. And think of this as x bar sub k minus x bar squared. Now, that would be if we had a single dimension. We have p dimensions, so you've got to do it over all p of those dimensions. But it's trying to characterize how different are the group means from each other. The within group sums of squares would be how far is each observation from the group mean. So add up the squared lengths of those lines plus the squared lengths of those lines plus the squared lengths of those lines, and you get SSE. So in one dimension, that would be SSE, or the within, is going to be the sum xi minus x bar k. So take an observation from group K and find out how far it is from that group mean. Finally, we'll use a pencil here. You're not going to be able to tell the difference probably between the red and the blue and all that. But the difference from every observation to the grand mean is going to be the SST. So we have the three sums of squares. If that's not clear, go watch my review of one-way ANOVA. Now, with one-way ANOVA, I reminded you that the total variance is the within plus the between. Well, there's another identity called the MANOVA, or multivariate ANOVA identity, which says the same thing. So the total variation in the data is simply the within variation plus the between group variation. So k-means minimizes the within cluster variation. Because the total variation in the data is fixed, you can also think of k-means maximizing the between group variance. So you can think of k-means either as selecting the clusters to make the within cluster variation as small as possible, or equivalently, you can think of it as maximizing the amount of variation between the cluster means. I'd like to mention a couple other things about this objective function. I've been talking about SSE as variation, and if we divide that by the degrees of freedom, we get a variance. Another way to think about this is squared Euclidean distance. Let's say that I have my x1 and I have my x2 axis. If this is the cluster mean, so let me just clearly identify this as x bar 1, because that's the cluster mean for group 1, and maybe I've got some points out here. Let's consider some x. So this is maybe x sub I as a vector. So all of these are vectors. So when I take x sub I minus x bar sub I squared, what I'm really doing is I'm finding the squared Euclidean distance between that observation and the cluster mean. So if you're not quite sure about that, let's just write out what we've done. We found xi1 minus x bar 1, that's the first component squared, plus xi2 minus x bar 2 squared, where this is x bar 1 comma x bar 2, not as a vector. This is xi1 comma xi2 as a vector. Well, what is this? This quantity is the length of that side. This quantity is the length of that side. So if I take the squared length of this plus the squared length of the vertical deviation, I end up with the squared length of the distance from x sub I to its cluster mean. Another metric that we'll use is to divide SSE by its degrees of freedom The way I like to think of this is it's kind of an average within cluster variance. If I were to go off and draw a picture of, say, two clusters, so I've got two clusters here. So if I find SST, and then I divide by the degrees of freedom, you can think of that as the standard deviation within a cluster. So it can be the standard deviation in this direction, it can be the standard deviation in this direction. All of these are going to have the same standard deviation. I should draw that a little bit neater. And that standard deviation, call it sigma, describes how much dispersion there is within each cluster. Now I called it the average because we've averaged the deviations in this direction with those in this direction, the deviations here and the deviations here. So this is a meaningful measure when you've got the situation where you've got round clusters of equal size. This measure is not as useful if you have clusters of different shapes. So if I had a cluster like this, I'd be averaging the deviations here within with the deviations in the other direction, and that's not very informative. I could have another cluster that's shaped like this, and so this average measure is not that useful. Well, having established the notation, let's go look at some real data. This data set has respondents from about 3,000 people in the greater Chicago area. It's a fairly old data set now. This is over 20 years old. We asked people on a survey 2 questions. How much time do you spend reading the paper each day? And the responses were divided up into 8 categories. So 0 meaning I don't spend any time reading the newspaper, all the way through I spend a whole lot of time reading the newspaper, and everything in between. We also asked, how many sections do you read? And so we listed 8 sections in this particular paper, and we asked which ones do you typically read on a given day, and that ranges from 0 to 7. What I'm showing in this picture is a kernel density estimate. It's kind of like a 2-dimensional histogram. So ordinarily with a histogram, we would use area to represent the number of people. So the greater the area, the more people with that set of values. Here, we're going to encode the density of people using color. So red means there's a lot of people sitting there. Blue means there aren't many people sitting there. So what we can see is there is basically nobody who spends a lot of time reading no sections. And so that ought to make a lot of sense. Likewise, there's almost nobody who spends 0 time reading all the sections. So you physically cannot get people in those corners. But if we look at what else we see here, I see 5 modes. So there's a mode down here. There's 4 modes in the main part of the picture. Here's the same plot in R using a contour plot as well as an image plot. Image uses grayscale to represent the same thing. I think this version of the plot, this one happens to be generated in SAS, is a little bit clearer. And so you have to think about if you were a hiker. If you were hiking, you'd have 5 mountaintops here, and the contours would show the height of those plots. The next thing we might want to do is to interpret these different modes. So I have a mode down here that's basically at 0, 0. I would call those non-readers. So they spend almost no time with the paper and they don't read any sections. When you look at the contours off to the right, you're going to see that's kind of like Mount Everest. This is a really high peak. Let's go to the other end of the plot. On the upper right, I have a group of people who spend a lot of time and they read all the sections. We could call them heavy readers. We have something in between. So we have a large group of people who spend a little bit of time and they're interested in just a couple sections. We might call those light readers. We also see 2 other modes that are perhaps the most interesting ones on the plot. So at the top we have a group that doesn't spend much time with the paper but has pretty broad interests. They read most of the sections. We might call those people skimmers. And it's very informative to know that there is a group of people who have skimmers. So you could think about creating touch points designed for the skimmer. It's very common to have newsletters, news briefings. So here is a list of the 10 main stories of the day, and I'm going to give you the headline and maybe one sentence about each. That's a touch point that's designed with the skimmer in mind. They're trying to make it easy for that skimmer to keep up on things. Back in the early 1980s, USA Today was launched. That was a revolutionary newspaper because it was really designed for skimmers. The stories were short, there were a lot of visual images, and it was just meant to be read very quickly. If we go to the bottom right, we have yet another type of reader who spends a lot of time with the paper but doesn't have that many interests. Maybe they're only interested in, say, 2 sections. So this could be someone who is the ultimate sports buff and spends a lot of time poring over every box score on the paper, but doesn't care about much else. So the point is, I see 5 natural groupings of data in the scatter plot. Can we recover these with cluster analysis? If I only have p equal to 1 or 2 variables, I don't really need cluster analysis. I can simply look at a histogram. I could look at one of these density estimates and spot the natural groupings as we have here. When I have more than 2 variables, though, it's much harder to visualize the data, and I really need cluster analysis to help me identify these natural groups. So to find a k-means solution, the first thing I would do is to set the random number seed. The reason for this is that k-means depends on starting values. If you use different starting values, you will get a different cluster solution. So there have been many times where I've run a cluster solution, then I want to rerun it and get the cluster solution again, and I can't get back to it because I didn't set my seed. So if you set the seed, you'll be able to regenerate your cluster solution. R has a built-in function called k-means. I pass it my X matrix. So NP2 is this n by p matrix with 3,000 subjects, 2 columns for my for time and sections. I give it the number of clusters that I want. So 5 is big K. The last 2 arguments are some extra parameters for the algorithm. The first one sets the maximum number of iterations to 100. So run the algorithm to convergence, basically, is what I say when I pick a big number like 100. As I mentioned a minute ago, k-means is highly sensitive to the starting values that you use. The second 100 here says, run the algorithm with 100 different random starting seeds and choose the best one. In that way, we hope that we found the optimal solution. K-means returns a list of class k-means. This list has the following components. So let's walk through them in order. So fit $cluster gives the cluster to which observation I was assigned. Another way to think about this is it assigns it to the closest cluster in the Euclidean sense. Because remember, we're minimizing the sum of squared errors, and those errors correspond to squared Euclidean distances. So the first 10 observations all got assigned to cluster 1. The centers argument gives the cluster centers. So let's go examine these on a graph. So I've actually plotted them down here. These big pluses are the cluster means. So the first cluster centroid is located at 0.28, 0.25. So if we look at our scatter plot down here, that's this first cluster centroid and corresponds to what we called non-readers earlier. The second cluster centroid is located at 2.47, so that's about 2.47, 5.3. So that's this red group. Those were our skimmers from before. The third cluster centroid is located at 6 point something and 2.67. So that's this green group, and that would be our group of selective readers. The fourth cluster has a center at 2.36, 2.1. That would be this plus and is made up of all the blue observations. Finally, the fifth cluster is located at 6.2 something, 5.9. That's this light blue group up here. Now, on my plot, the plot command that I used to generate this is given below. So I jittered, meaning I added a little bit of noise, since these were all discrete values, time, and sections. So time on the x-axis, sections on the y-axis. I'm encoding the cluster assignment as color. So the way to think about all of these blue observations is that the closest cluster centroid is the one that I'm hovering over. So this group of points is closer to this centroid than any other. Likewise, the two black clumps are closest to this big one. The reason this centroid is much closer to 0, 0 is there's a lot more 0, 0s than there are 1, 1s. So when I average all those cases, the mean drifts towards 0, 0. By the way, I use the points command to add the cluster centers. So moving on, the next component in this list is the within sums of squares. This is going to be the sum of squared errors between every observation that was assigned to a particular cluster and the cluster centroid. You can also think of it as the sum of squared Euclidean distances. If we add up those values, so here I just sum them, we get another part of the list. So that's the total within sums of squares. This is the objective function that we're minimizing when we fit a k-means clustering solution. So sometimes this gets called the clustering criterion. The overall quality of this solution would be 4169. Think of that as the sum of squared errors in regression. Moving on, the size gives the count of observations assigned to each cluster. So this would be the same as if I just ran a table on fit$cluster, but since this is one of the things that you always want to look at, k-means just stores it in its output. If you flip ahead a couple pages, I've written some functions that I often use when I interpret a k-means clustering solution. So there's a function summary.k-means. Whenever you type summary, it looks for the class of that object, and if this one has a class of k-means, it's going to use this code to summarize it. So let's go take a look at what's in my summary. So my summary gives the basic frequency distribution showing the number of cases, but often we're more interested in the percentage of cases, so I just compute those. So we could say that 17% of the cases get assigned to cluster 1. Next, I report the mean values for all the variables in the cluster analysis. So you'll see the same means that I had before, but without as many decimal places. Usually you don't need 8 accurate digits, you only need 2 or 3. Finally, I've computed the within cluster Rmse. So Rmse is the within group sums of squares divided by the number of dimensions times the number of degrees of freedom. Think of this as describing the within cluster dispersion. If we look at cluster 1, the within cluster dispersion is far smaller than for the others. I think that's quite obvious from the plot, because only 2 values got assigned to that, and most of them were 0, 0s. On the other hand, cluster 2 has the largest within cluster standard deviation. So cluster 2 is the skimmers. And we can see that 16 different values got assigned to that cluster, whereas all the other clusters had fewer values assigned to it. So it's entirely plausible that that within cluster standard deviation is going to be substantially smaller. I also report the clustering criterion. I compute an R² value. I also compute an F statistic, which we'll talk more about when we discuss selecting the number of clusters. In addition to this overall standard deviation, it's also useful to look at the standard deviation by X variable and by cluster. I haven't included that in my summary function, but you can easily do that with a little bit of dplyr. So if I group by cluster, I can find the standard deviation of time and the standard deviation of sections. And this would help me detect if I have a cluster that's elongated in one way or another. So for example, let's go back to cluster 4. Cluster 4, remember, is this dark blue one. We'd expect the standard deviation of hours to be a bit greater than the standard deviation of sections. And we see that's the case. So the standard deviation for hours or time, there's more variance in this direction than there is vertical variance. Alternatively, with cluster 3, so cluster 3, if you remember your R colors, is going to be the green one out here. You can see there's more variance in the vertical direction than there is in the horizontal direction. With cluster 2, the red one, the variance, the standard deviations are the same in both directions. So in summary, when you run a cluster solution, the first thing you care about is the cluster means. Second thing you care about is how big are the clusters. Then the third thing you start to care about is the shape of the clusters, which can be described by these within cluster standard deviations. This next slide shows how to run k-means in Python. There's a k-means implementation in scikit-learn. It looks fairly similar to what we had in R. Let's now do another example. So hopefully at this point you understand the link between the two-dimensional scatter plot and the cluster solution. Now let's take it up another dimension where we have p equal to 3 variables. And it's going to be a bit harder for us to visualize things. Therefore, we're going to really have to rely more on the cluster output. A few years ago, I worked with a trade show that happens here in Chicago at McCormick Place. And we got data measuring why do people attend this trade show. We'll talk more about these 3 dimensions when we get to factor analysis in the last week of class. Basically, there are 3 main dimensions for why people attend. One reason is that they come to this trade show to buy something. The trade show attracts all the major vendors of whatever the trade show is about. And so if my company has a specific need and I want to go see a lot of different solutions and talk to a lot of reps, one of the best things to do is to go to McCormick Center, and it's everyone is there. Another reason that people go to a conference is for social reasons. So perhaps they want to meet up with other professionals in the industry, they want to build their network, or perhaps just renew old friendships. A third reason is more around education. So every day there's a keynote speech that talks about some important issue for the industry. There are numerous breakout sessions. So I actually attended this one. There was a breakout session on how big data and AI was going to revolutionize material handling solution problems. So you can get an education from attending such talks or just walking the floor and talking to the representatives about their solutions and what's new about their solutions. So we had a sample of people who attended this trade show, and we asked them, to what extent did you come to buy something, to do these social things, to do this education? So notice I have p equal to 3 measures on each of my respondents. And let's go find the 3 cluster solution. So this is the way I would run it in R. I'd set my seed. I'd say, go find me 3 clusters. And here's the output. So I could start by just interpreting what comes out of my summary function. When you interpret these, you usually want to compare across the means of a dimension. So what I see here is cluster 3 has the highest mean on buying, whereas cluster 1 is comparatively low on buying. On the other hand, clusters 1 and 3 both have a pretty high mean for social. Cluster 2, on the other hand, is not really coming to the conference for socializing. They're coming there for something else. When it comes to education, we can see that cluster 3 has by far the largest mean in education, while clusters 1 and 2 both have relatively large values, but small compared to cluster 3. So the way I would interpret this is cluster 3 is coming for the full conference experience. I'm not sure Cluster 3 is ever going to sleep, so they're going to spend a lot of time on the floor looking for stuff that they can buy. They're going to be socializing as more than any other group, and they're going to attend every educational seminar they can. On the other hand, Cluster 1 is much more interested in social and less interested in buying. The opposite is true for Cluster 2. So Cluster 2 is a little bit more interested in buying, less interested in socializing. It looks like all of my clusters have roughly the same amount of spread. So the next page shows all possible scatter plots. So we have social versus buy, education versus buy, and then education versus social. I think the clearest version of this is the social versus buy, and everything I just said on the previous slide becomes pretty clear here. So the green, Cluster 3, is very high on social and buying. You can see that the red cluster is high on buying, not so much on social. The black cluster is pretty high on social, not so high on buying. Another plot that I like looks a little bit like guitar tablature. And this plots the mean for each dimension in each cluster. So it's a multi-panel dot plot. So I have one panel for each cluster, and I show the cluster means. You could look in more detail by showing box plots. That would also capture the standard deviations. But let's just stick with means. So clearly Cluster 3 is high on everything. Cluster 2 is not as interested in social. Cluster 1's really interested in social, but not interested in buying. So that plot is created by my plot function, which if you just say plot fit, you get that multi-panel dot plot from it. So at this point, I hope you have a good understanding of how you run and interpret k-means in R, and Python's pretty similar. The next video is going to get into some of the decisions that you have to make along the way.